Today, let's go on a journey to explore some of the challenges related to the recovery of hydrogen from common waste materials. Hydrogen is designated by the elemental symbol of H2. The Recovery 2.0 system is an innovative approach to manage the treatment of residual waste materials in a sustainable method, by treating waste as a resource, while assisting with the world's demand for clean water and clean energy by using thermal reduction. Within the Recovery 2.0 process, we have focused a great deal of effort on energy recovery in an effort to manage the energy continuum while attempting to maintain a balance or equilibrium with our environment. We are going to look at the three most common methods to produce hydrogen. The first two methods both involve the recovery of hydrogen from a water source, and the third method extracts hydrogen from hydrocarbon compounds. Current headlines that spotlight decarbonization and the movement towards a hydrogen economy tend to feature green electrolysis to split water into hydrogen and oxygen. A less popularized method that we also rely upon to produce hydrogen is the chloralkali process of brine electrolysis. Other industrial processes use thermal methods that release hydrogen from water or steam. The Recovery 2.0 system taps into the benefits of both the water-gas shift and metal redox reactions. In the third case, hydrogen is sourced by hydrocarbon cracking to release hydrogen from various hydrocarbon compounds. Some hydrogen production operations use a combination of methods, such as steam methane reforming, to generate hydrogen. The popularity of the idea of shifting to a hydrogen economy has spawned some new and innovative attempts to develop novel pathways towards hydrogen. In many hydrogen production schemes, dealing with storage and transportation issues dominate their thinking in an attempt to reach a market. While it is an option to produce hydrogen for external sales, within the Recovery 2.0 process, we focus on the internal consumption, to use hydrogen as a reactant. Primarily in the CO2 management strategy, we use hydrogen or H2 to perform a synthetic methane conversion. And then implement further processes in a CH4 pyrolysis step, to convert the methane into solid carbon. We are able to overcome or avoid the complexity of large-scale storage and transportation issues, with the almost immediate local consumption, if and when the H2 is recovered. Any discretionary storage can be designed at a smaller scale for short-cycle regeneration. The thermal reduction of waste materials in the pyrolysis process potentially produces an ongoing flow of recovered hydrogen. This flow rate may be treated like a base load, and may feed synthesis reactors or fuel cells. Capturing the flow of hydrogen that is generated from electrochemical flow cells, or redox reactors, during high-temperature steam decomposition or oxidation procedures, provide an example of thermochemical water splitting. This involves reacting metals such as aluminum, magnesium, or iron with acid solutions or high-temperature steam, often at temperatures in the range of 900 to 1200 degrees Celsius, in a reactor, to produce hydrogen and metal oxides. Solar, wind, and other sources of intermittent and variable energy may be used to power the electrolyzers, in order to split water. Using battery storage banks allows for the distributed or buffered output of the intermittent sources to power the electrolyzers. Utilizing battery chemistries, such as iron or nickel-iron batteries, that utilize water-based hydroxide electrolytes, you may be able to take advantage of the unique properties of these devices to adapt to intermittent power sources. If you maintain a balanced inflow of clean water, by overcharging this particular design of battery, it is compatible to seamlessly swap these devices into electrolyzer mode, producing hydrogen and oxygen when surplus electricity is available. By designing a bank of electrolyzers and battery storage sitting at the ready, you have the potential to provide the capacity as an electricity sink, with the ability to absorb excess intermittent energy and avoid curtailment. Accumulation of any generated or recovered hydrogen into buffer wells that incorporate expandable bladder piezoelectric harvesters, you may generate a small amount of energy from the overall flow. If required, additional temporary storage reservoirs, under moderate compression conditions, with no particular need for cryogenic storage, may be designed. The temporary storage reservoirs allow for the discretion to dispatch the bank of hydrogen, where and when it is required. Since most common waste streams are hydrocarbon-based, including wastewater, brines, wood, paper, textile fibers and plastics, we view these waste materials as a largely untapped source of hydrogen. The recovery of hydrogen and other essential resources, on a small scale or local basis, may be attractive in niche market applications, and may fulfill a desire for an independent supply, or to fulfill the requirements or need of a secure supply chain. Small-scale modular recovery systems may never reach an economy of scale on an industrial production level and therefore, may never be competitive across broad or general mass markets. In summary, the generation of recovered hydrogen from resource recovery applications may achieve the threshold by overcoming the challenges and become a reliable strategic supply source. We intend to discuss additional facets of the energy and resource recovery sectors at some point in the future. Until then, please feel free to contact us at your convenience. Recovery 2.0 is a project developed by Waste.net, in an effort to reinforce our belief that as rational human beings, we must accept the ultimate responsibility to leave future generations with a safe and sound environment, and a world that has not been depleted of its resources. Please feel free to visit us today at www.waste.net.